All right, we should be live for WorldQuant office hours. So welcome everyone to WorldQuant office hours. I see Sabine is here. All right, let's see. I see Ramsey is here. So there's some discussion about time series and hyperparameter tuning in neural networks. So we're going to go through and continue on talking about neural networks. So we'll definitely touch upon those topics today. I see Ramsey is here. I see Renato is here. Welcome everyone to WorldQuant office hours. Hope everyone is doing fine today. Okay, let's see who else is joining us so far today. I see Mickey Rat is here. Now, I want to start off with today with our discussion of neural networks. I'm going to rename this the office hours, I think 22 November. I think that's the style I've been doing. Yeah, it's at least so far. All right, there's still a strange echo. Let's see if I can fix that. Okay, anyone else seen a strange echo? Just want to know how widespread this problem is. How about now? Is it better now? Is it better now? Do let me know. Okay, a lot better. Okay, good to hear. Good to hear it is a lot better. Thank you for that. All right, so let's go ahead and pick up our discussion of neural networks, and let's go and talk about what we've done before, right? We talked about what are neural networks and what is deep learning, the math behind deep learning, the math involved for making predictions, but also for training the algorithms, training those neural networks, those models. And we saw this idea of the chain rule, and that's called automatic differentiation. It's got a different name in different fields, but essentially how we train these algorithms is by applying automatic differentiation, basically the chain rule, to come up with an expression on the derivatives of the loss function with respect to the model weights. Now let's actually build our very first neural network model. We're at that point there. We've done TensorFlow, right? We talked about the fundamental data structure of TensorFlow, of those TensorFlow tensors. We contrast it with NumPy arrays, but now let's actually build a neural network model using TensorFlow. So we import TensorFlow as TF, which is customary. And we're also going to, from TensorFlow, we're going to import Keras. I'll talk about what Keras is exactly when we get to use it. Call those imports. I'll probably get some warnings saying I don't have the GPU set up. That's perfectly fine. And let's work with the data set. Let's go ahead and pull out a data set for us to work with. And what's very classic for getting introduced to neural networks is to solve the problem of digit classification. We have 1, 2, 3, 4, and so forth. So train an algorithm to predict what digit is shown in an image. But let's actually do something slightly different. That's been done way too much. Let's look at a slightly different problem. And let's go ahead and say from Keras is going to provide us some data sets. So we're going to specifically look at the data set called fashion MNIST. So we'll call this fashion MNIST. And we will say xtrain. So here's just loading up the data set that we're going to play around with. We also have a test set as well. Fashion MNIST, load data. Let's take a look at that data. Let's take a look at our training data. want to look at one of those observations. So we have 28 by 28. I see Raymond is here. Welcome, Raymond. We have 28 by 28. Well, let's look at what exactly is the shape of training data. Interesting. It's a three-dimensional array. I can look at the data type. What is this? What is xtrain? Well, xtrain is a NumPy array. It's a three-dimensional NumPy array. And the reason why it's a three-dimensional NumPy array is because we have images. So we have the width and the height, which are 2 dimensions, but the third dimension represents a different image. The third dimension represents a different image. So we have height, width, and the number of images. So that is why we have a three-dimensional array. That is our data. I see Dara J is here. Welcome, Dara J. Okay. Questions about the nature of the data we're working with here? Well, let's visualize this data, right? Let's visualize it. We have it here, but let's visualize it. So what I'm going to do, I'm going to import matplotlib pyplot as PLT. I'm also going to import time. What I'll do is that for I in range of 50, let's just sleep for 2 seconds, and let's show one of those images. I call the imShow function, which is a way to show an image, because that's what we do. We have multiple images in our training data. And let's use a grayscale gray. Let's see what we've got there. All right, so these are our images. This is what we're getting out. One looks like a shoe, that looks like a shirt, this looks like a dress, another dress, a shirt. Let's see what else we've got. Another shirt, a shoe, a shirt, a shoe, another shoe. So notice we have various grayscale images of what appears to be articles of clothing. When you say the number of images, is it different images or different colors of the same image? There are different images. So we have 60,000, that dimension is each one of those is an image. So 60,000 images. I am showing just 50 of those. So the reason why I have a three-dimensional array is because I have height, I got width, it was width, height, and then on the other dimension, so width, height, and the dimension into the page or into the screen is the number of images. And since I have grayscale, I can represent the image using one number for every pixel. So I thought MNIST only contains digits from 0 to 9. So this is a different MNIST data set, right? MNIST stands for something national, Modified National Institute of Standards and Technology. So there's the classic MNIST data set for digits, but there's also an offshoot that is actually of articles of clothing. So it's different from the classic one we're used to. In fact, let's see. Take a look at that information. Yeah, so it's supposed to mimic, the reason I think it's called MNIST, is it's supposed to make a lot of references to the original MNIST that it said that was, as you pointed out, bioinformist, was indeed just digits. In fact, we can go into the source. See, so the drop-in replacement to the original MNIST data set. Yeah, so here's some example of those images. And some nice, interesting visualizations of this here. Okay. And they explain why they made this other data set. Other questions people have? Okay. Let's see. I see a question here. Is the data set pixelated, or did you do that? Well, all images are not all images are pixel, but it is only 28 by 28, right? These images look very pixelated because they're only composed of 28 pixels height and width. So we don't have much resolution for these images. So when we look at them, we definitely see them that they are pixelated. The original data set, if I look at here, doesn't quite look as pixelated. It just might be, this might be the original data, and then they've only pulled out a 28 by 28 resolution of it. Or it could just be that this is so far away, we aren't able to distinguish the individual pixels. But it's a rather, let's see what they've got here. Interesting stuff. Okay. All right. Other questions you have? Okay. Well, do let me know. But let's go ahead and build our very first neural network model. So we saw that we imported Keras, and you might have heard what Keras is. But Keras started a while back when TensorFlow was in its rather infancy, which was a lot more tedious to work with TensorFlow back then. It wasn't quite user-friendly. So Keras was this third party that said, you know what? We're going to build a nice interface or a nice API to TensorFlow. And not only that, but they built it so it can work with other frameworks. And because of its popularity, ultimately TensorFlow adopted Keras into the official TensorFlow distribution. So that's how we are going to import Keras. It's going to make it a lot easier for us to create our models. So let's try that out. So there are two key ways we can construct models in TensorFlow using Keras. There's the sequential API and there is the functional API. We'll see both of them and we can contrast between them. But the very first thing we do is we create a model. So Keras model sequential. So we've created a model object. But this model object doesn't have any layers. Think of it as just a blank slate. Now what we've got to do is we've got to add layers to our network. Now the first thing we got to do, so let's go ahead and draw how our model will look like. Let's talk about how our model will look like. So we will have these nodes here. Any number of these nodes. We will have a hidden layer. We will have a second hidden layer. And then we'll have an output layer. So here's the input layer. Here's the hidden layer 1. Here is hidden layer 2. And here is our output layer. This is a network we're going to draw. Now I'm not going to draw their connections because there's just way too many to draw, even just a few that I have here. But you can imagine that every node in this layer is connected to every node downstream. We won't draw the connections, but you can imagine that's what's happening in this system here. So that's what I want to have here. Now, do you recall what that input layer represented? What was that input layer all about? What was it? What was that input layer? Do you recall? Yeah, it gives the initial data to process, right? So that input layer represents the initial data, right? The original features of our data. But we haven't quite talked about how we take pixels, how we create an image, and what are those features? Right, what are those features of our image? So we have an image here, and I would draw a pair of pants. There's our image, but it's pixels. It's composed of pixels. Composed of pixels. Any number of pixels. And for our problem, we have 28 by 28. That's the system we have, 28 by 28. So what this means is that every pixel is a feature of our data. So what we do is we take the pixel, and that goes into this node here. We take the next pixel, and that becomes the next node there. We take the next pixel, and so forth until we get to the very end. So every pixel represents an input node. Remember that the input layer is dictated by the number of features we have in our data. So if we have 1,000 pixels, our input layer will be 1,000. So the first thing we got to do to work with our data is we got to take this image and we got to flatten out the image. We got to take this image and we got to flatten it out. And that's what we do. That's the first layer we do in our model. So we're going to add a layer to our model. We say model add, and we give it the layer we want to add. Keras layers flatten. And we'll put the input shape. The input shape is 28 by 28. So this adds a layer into our network that will take an image and flatten it out. Now my question to you is, what do we lose when we flatten out an image? What do we lose when we flatten out an image? But physically, we lose shape, right? We lose shape. But what do we lose beyond shape, right? I do agree with you that we lose the shape of the image, but what do we lose? A little more fundamentally, we lose. It's a 1D array, right? Correct? We lose a dimension. We lose something with a shape, so we go from 2D to 1D. But what do we lose when we go from 2 dimensions to 1 dimension? What do we lose when we flatten out an image? Something else, something we are losing fundamentally. we're not losing columns, because if we go from something that's 30 by 30, we have 900 pixels, we have 900 elements in that one dimension, so we're not losing columns or features, but we are losing some amount of information. If I flatten an image, I'm losing some spatial information. I'm losing some sort of spatial configuration of those pixels. Right? So if I take this image here, and I were to flatten it, then I've lost the arrangement, the relative position of a pixel relative to other pixels. And now that I flatten it out, I lose that information. So maybe flattening out our image isn't the best thing to do. All right, we'll go ahead and do it here, but we will talk about a different model that will solve this problem that we have of losing some geospatial information, some spatial information about our pixels when we flatten it out. We'll put a note of it. We're not going to solve it here today, but we'll come back to it later when we talk about other architectures of neural networks. Okay, we'll keep that in mind. All right, we flatten it out. The next thing we do is we have our hidden layer. And just for right now, we're going to say our hidden layer. So the number of pixels here are 28 by 28, right? The number of elements in this layer is 28 by 28. In the hidden layer, we're going to say 100. And we're going to say 100. Let us not worry about why we chose 100, right? The point of here is not for us to get into those nitty-gritty details right now. For us, it's just to construct our very first model. So this object is mutable, so I can call model add. Let's add a new layer. Layers, and since it's a dense layer, in other words, all the nodes of this layer is connected to the previous layer, and all the nodes of this layer is connected to the next layer, it's a dense layer. So say dense, we'll say 100, and then we got to choose an activation function. Remember what we use an activation function for. We summed up the values, then we run it through an activation function. And here I'm going to say the sigmoid activation function, which is used for logistic regression. And once again, let us not get stuck about why we've chosen sigmoid. That is not the point right now. And then since I want a second hidden layer, I can call model add again. Keras, layers, dense, 100, activation, sigmoid. Okay. Any questions so far? Okay, so we save a question here. What is dense 100 doing? We are saying we're creating a layer that has 100 neurons. And dense is a type of layer. What it means that all that layer is connected to all the neurons in the previous layer and all the neurons downstream. So why 2 of 100 instead of 1 of 200? All right, we'll go and save that for right now. We'll go and push that for right now. Put it away. But it's a good question. And we had 28 by 28, so 784 pixels. Yeah, exactly right. There's 784 pixels for this layer. 784. We've constructed this layer when we said flatten. Do neural networks will be independently trained on every image, or will it process all the data at once? Do neural networks will independently train on every image, we train on a batch of images. We'll train on a batch of images. We'll get to that later. So a couple things that we still have to talk about, for example, why 100, 100, why not 200 and that's it? Anything else we want to bring up right now? Isn't the second layer supposed to have lesser neurons than the first hidden layer? Not necessarily. Not necessarily. Anything else we want to bring up? Anything else we want to bring up? Okay, let's go and move on. The last thing we need is we need that output layer. So let's go and flesh it out. So we need that output layer. But the thing about that output layer is that output layer, the number of neurons for that layer is dictated by the number of classes we have in our problem. And for our MNIST dataset, this fashion MNIST, we have 10 different classes. It wasn't quite so clear, but if I look at, let's say, ytrain, I guess I could call set on it. I have 10 classes. So my output layer will be 10, but I'm going to use a different function for the activation. I'm going to use the softmax activation function. Now what that softmax activation function is going to do is it's going to take what gets summed up in the sigmoids, now what gets summed up here, and it's going to run each of these. It's going to output a value, but it's going to be normalized the following. Probably best write out mathematically what's going on there. So I'm going to say the softmax value, which is a probability of class K, is e to the, I'll call that zk, over the summations of e to the zk. I'll make different variable I. Number of classes I have. This here is the softmax activation function. And the reason why it's called the softmax activation function is because it sort of acts like a softer max. In other words, what could have happened in this situation is I could have had, let's say for example, I had let's say I have a value of, let's have a value of, let me go put some numbers in there. Let's see, what type of numbers should I have? We have numbers 1, 2, and 0.5. Well, if I were to apply a hard max, well, that means that this is the answer here. So if I were to apply a hard max, this will go to 0, this would go to 1, and this would go to 0. So I made the largest number become 1. That's a hard max. Whatever, since 2 was a max, it becomes 1. That's a hard max. But why don't I use something that's a little bit softer, so to speak. So while 2 will be highly promoted, it won't be promoted as much, or not so strongly. So let's play around with that. I can say import numpy, right? Import numpy. Once I have my array, np array. I think I've import numpy. I have not, probably. And I can go ahead and take array of z's, and I can say mpx z and compute the sum. So notice there what happened is that 2 was still promoted, was still the largest value, but now I've distributed some amount of probability across the other classes, the other indices. So instead of taking this one saying here, making bit 1, I'm saying what, there's some probability of it being this class or that class. So it's a softer type of max. It's called the softmax activation function. Yeah, softmax seems, softmax is one way to view it. Softmax is a way to scale the values between 0 and 1, right? You recognize this piece here as a normalization piece. This is a normalization piece. Normalization. So that the sum of all the values in the output will be 1, which makes sense because we can treat those values in the output layer as a probability of being in that class. But instead of looking for the one that had the largest value and saying that is purely 1 probability and everything else is 0, that's a hard max, let's use a softer max. And that's why softmax is used. And the other benefit of softmax is that you can actually take the derivative of this activation function. We know what the derivative of this function is. We can write it out mathematically, not an issue. Questions you have? Okay, we'll go move on, but do let me know if you have any further questions. Okay, so we'll go in back here and we'll add our softmax activation function, and it's of 10 because we have 10 classes. And that constructs my model. I have my model there. Well, what do we do with that model? Right, what's next? What do we do with that model? But before we actually do anything with the model, wouldn't it be nice for us to kind of come up with, understand how many model parameters we have to solve for? Let's understand how many model parameters we have to solve for. Well, we have the weights from the input to the hidden layer 1, right? In other words, this here. This here. There are 784 nodes, and they're connected to 100 other nodes. So that means that the number of this matrix here is going to be total weights, we 784 times 100. Plus, we cannot, about the other layer, which is, so we have, in other words, we have W of 1, and we have W of 2. And this is 784 by 100, and this is 100 by 100. So 100 by 100. Where did the number value 10 come from? The value 10 because we have 10 different classes. If I call the set on Y train and take the length, I got 10 classes. So that's why that sets the number of nodes in my output layer. The number of nodes in my input layer and the output layer are the easiest thing, because the input layer is how many features I have, and the output layer is the number of classes I have. What goes in the middle is a design choice that we're building up to, but we're constrained by the output class, by how many classes we have, in this case, 10. So let's consider the number of weights that we have. So it's 784 times 100 plus 100 plus 100 times 100, right? This is W1 and W2 matrix. What about the total biases? And the biases is that plus B term. So let's rationalize what we have there. Well, we have, if we look at our situation here, let's see, we're going to have one bias for every input, a plus B for every of these neurons. Okay. So we can go ahead and say, let me just double check that right here. W is my weight there. Meant X. X is number of rows and columns. Here times number of features I have, and my design choice about the size of the hidden layer. That's why W1 is 784 by 100. And then I should have a bias term, K of B, B of K. So total biases there should be 100. And then we add the other bias term, which should also be 100. And we get total parameters, total weights, plus total biases. I think I might be off here, but we'll see. We'll see. Where did the value? Okay, I already answered that. And let's go ahead and look at what we got next. We can print out the total number of parameters. That's close to almost 100,000 parameters we're dealing with. Right? Think of it, the other models we've done before, those traditional ML models we've played around with. Not nearly as many model weights we're trying to solve for, or model parameters we're solving for. We're trying to solve for nearly 100,000 model parameters. We'll keep that in mind. In fact, if I call model and I call the summary method of my model, it shows me a summary of how my model looks like. It tells me how many layers. We have a flattened layer, a dense, right, 2 dense layers, followed by a third dense layer. And we have there is the number of parameters that are in each of those layers. And specifically, it tells us the total number of parameters we have all together. So 89,610 total parameters. Now I must have goofed in my arithmetic here because I don't have that same number. So I probably messed up somewhere in the biases. Let me think about that. You have your input layer, and you have a weight that associates how much strongly to have each feature tied to each hidden layer node. So somehow I'm messing up there in my arithmetic. Let's see. To think about it a little more, but oh well. At a close estimate. No weights between the second layer and the output. Right, so we have no weights between the second layer No, correct. No weights between the second layer and the output, because the reason why is because these values we have here get fed automatically to the softmax activation function. So to sketch out that math, what I have here is, at that point, I have something like A of I of, let's say, K times W of K L. This is of the second one. And this is Z of I of L. And this gets fed to the softmax. If you add them, then the param calculation would work through, right? Oh, there is a bias. Oh, there's a bias here. Right, there's a third bias. Did I mess that up? Now I'm erasing stuff. I have a bias there. I'm still erasing stuff like crazy. All right. I got my weight there, so I got a bias, and there should be, I think, still a bias in the output. So maybe that's where I'm messing up. There's 10 biases here. And let's see, that's a little more, but it still doesn't solve where I'm missing the other ones. Let's see. Must be missing some, but oh well. Let's go ahead and move on. Right? Actually, in fact, I can look at each layer. Will tell me the number of parameters in each layer. Okay, any questions people have? Okay, so the next thing I do is, well, I've created my model. The next thing I do is got to compile the model. So next, let's compile the model. So what does it mean to compile the model? What we do is we assign a loss function to the model. Remember that there's a loss function that we must minimize when we train the algorithm. So we must assign a loss function. We also needed to give it, an optimizer. Choose an optimizer. Remember, the optimizer is how to solve for the weights. So we give it, here's a loss function that must be reduced. Here's the optimizer that you will use to reduce that loss function. And the last thing we specify when we compile the model is any metrics to display when training. Those are the three things we must specify, or we can specify when we train the algorithm. Okay, so let's go ahead and compile our model. So the way to do that, we say model, we say compile, we give it the loss function. We're going to say sparse categorical cross entropy. The reason we're using this loss function, this is the loss function we use when we have more than two classes. The reason it's called sparse is, confusingly, is that our labels are not one-hot encoded. Our labels are not one-hot encoded, so we're going to use the sparse categorical cross entropy. Think of it as just a variation of the cross entropy we saw for logistic regression. We choose our optimizer, and we're just going to use plain old stochastic gradient descent. Let's not worry about the different optimizers, because there's a plethora of choices. Let's just get focused on getting something that works. And then we can talk about all the other things that we got to consider when we create our model. And the metrics, let's display the accuracy when we train the algorithm, when we train the model. And now we've compiled our model. Okay. So now we've compiled our model. We got to fit our model. So one of the things that we'll see about the Keras API, that it's very similar to the scikit-learn API. There's some differences. We're going to point out those differences, but we should feel at home when we use the Keras API. Model fit, X train, Y train. Very much just like out of scikit-learn. However, we're going to specify a couple other things in there. We're going to specify the number of epochs. So what is an epoch? Well, we have a ton of data. So we cannot apply true gradient descent or full gradient descent. In full gradient descent, you use the entire array to estimate the gradient. So instead what we do is we take a batch of data, a batch of the observations, and we use that batch to estimate the gradient. So let's not use all 60,000 observations. Let's just use a batch of data to estimate the gradient. And one epoch is one cycle of going through the entire training data. So in other words, if we have, for example, 60,000 observations, and we use 30 observations at a time, well, we do the math. We're going to have 2,000 runs, 2,000 batches for every epoch. So one epoch just refers to how many passes of the data we go through. We can't train on all 60,000 observations, so instead we just train on 30, 30, 30, 30, and as we go through the entire training data once, that's an epoch. So we say, how many epochs should we have? We're going to say 30. Once again, this is something else that we're not going to worry about right now how to set it. But hopefully you start seeing, wow, there's lots of things I've got to set and determine. This is one of the reasons why is we don't jump to neural networks right away. They are more difficult to train and to properly tune and create. In fact, our performance we might get up can be just a little bit better compared to more traditional models. And we just wasted our time, frankly. Is this equivalent to k-folds? It's not equivalent to k-folds. Because with k-folds is we actually finish training the algorithm. And we do the training across multiple folds. Here we are continuously training the algorithm. We call fit. It's going to be a rather complicated training process. We apply gradient descent. And we keep on, and when we apply gradient descent, it's a function of how many iterations we perform. And that's what the epoch is telling us. That's what the epoch is telling us. How many runs through the data we are performing for training, for one fit. So that's the number of epochs there. And we're going to say, last thing we say is validation split. 0.2. So in other words, what we're going to say here is, hey, use 80% for training and use 20% for validation. Very much similar to what we're used to in scikit-learn, right? Or this whole idea of machine learning. Train on training, but let's see how well you do on validation. I see a question here. What kind of parameters are considered as non-trainable parameters? Good question. So what might happen is we might have a situation where I am taking a neural network, but I only want to train part of the network. I have the full network, but I only want to train a part of the network. The reason why I might want to only train one part of the network is because that's the part that needs a little more specialization. It needs a little more specialization and attention given my problem I'm trying to solve. So what I got to do is I got to freeze all the other weights, all the other parameters upstream. So they're weights, but they're not trainable. So they're not going to be changed when I train the algorithm, train the model. So non-trainable parameters are those that we freeze because we don't want them to be changed, to be modified as we train our neural network. I'm going to go ahead and run this because it's going to take a while, but do let me know if there are other questions. And let me just show you what's going on here. We're going through our epochs, and we're showing you how long it takes, the loss, the accuracy, the validation loss, and the validation accuracy. It's a little different in scikit-learn in fact that by default it's showing us what's going on with training. Why did you call this an API? I call it an API because it's an application program interface, right? It's a interface that we apply to a program. It's an API. API is a rather generic term, right? It's basically an interface or a set of rules to interact with the program. And that's what it is. Just like we know about the scikit-learn API and the pandas API. All right. It's going to keep on going. Now let that continue on. We're training our very first neural network model. Is the loss val typically below 1? All right, so validation loss is below 1, and the validation loss is the cross entropy. And let's see, is it always, not necessarily, right? It could be greater than 1. It could be greater than 1. It just depends on, it's sort of like saying so validation loss is sort of akin to mean squared error, where it's a little difficult to really grasp because it's dependent on the size and nature of our data. So in fact, right, we see our loss is in fact greater than 1. So this is just more of a, just the way it happened to be. But any kind of peculiarity when we look at our data, our loss here is the training loss, and here is the validation loss. I think that's a little weird, a little peculiar when we look at that data. Okay, so one thing I want to point out here is, wait a minute, our training accuracy is lower than our validation accuracy. Our training loss is greater than the validation loss. Isn't that a little bit weird? We're sort of used to how your model does better in training than in validation, right? Because that's the data you saw, that's the data you trained on. You'd expect it would do better than on a validation set. So what's happening here is sort of, it's a bit of an unfair comparison between the two. What the algorithm is doing, or sorry, what Keras is doing is that this loss and this accuracy is the average across all the batches in the data. So from batch 0 all the way to batch n-1. It is the average loss and the average accuracy across all the batches it used for that one epoch. So that means that early on in the epoch, we had pretty bad results. We got better and better results as we go through the epoch. So we should expect that this average is an average. It's an average of what happened in the beginning and what happened at the end because it's an average. What's shown in validation loss and validation accuracy, that gets calculated at the end of the epoch. So, of course, the model will do better on a validation set that is performed at the end of the epoch as opposed to the average across the batches of the training data. So that's why we get this weird peculiarity for the first couple epochs. It appears that a model does better on validation than on training. But that's just because this loss is an average across the batches. And the validation loss and accuracy is only calculated at the end of the epoch. So is the loss with the training data and validation loss with 20% of training data correct? What it is that 80% of the training data is used for training, and 20% is used for this validation. That's what that means there. Okay. And that ran. And remember in scikit-learn, in scikit-learn, fit returns the object itself. But in Keras, in TensorFlow, fit returns a history object. So I didn't save that. Object. I'll say result equals underscore, and call it type of result. It's a history object. History, and this is a dictionary. It's a dictionary. It's a dictionary with how it performed for training. So in other words, I can say plt plot, and I can go ahead and say I want to plot results history loss. There it is. There's our loss as number of epochs. I can repeat again, but I can go ahead and show the what else? Let me show the val loss. Right, so here's my training loss and my validation loss. So notice it looks like it converged around maybe about 5 to 10 epochs. They rather converged. And finally, the last thing I want to show you for today is I can call the evaluate method. And let's see how well it does. So the evaluate is equivalent. So this is equivalent to score method in scikit-learn. We call the evaluate, and what it is here is the loss, the cross entropy loss, and here is the accuracy. So we're about at 74% accuracy. So not great, but we could probably do a better job. Any questions we will have before we wrap it up? Our emphasis here was just to create a model. And then tomorrow we can talk about all the bells and whistles that one must consider when we start creating these models and start tuning them. But any questions we want to bring up of what we've done here today? All right, we'll pick this up tomorrow and we'll talk about all the things one must consider, all the design choices we have in these in these neural networks. But hopefully you get a better appreciation that these things are not necessarily the first thing we want to gravitate towards, right? Because they are complicated, but they are powerful, right? With great power comes with great responsibility. We'll pick that up tomorrow